So that's A. Now let's move on to B. So what we have here is this is the change in region 3. Let's go back to our schematic. Where was it? Yeah, way up here. So region 3 was this region here. So what we're expressing is the time rate of change of our extensive property, because we're talking about capital N here, with respect to time. So what we're going to do, we're going to take advantage of this little subregion to be able to come up with an expression for the time rate of change of our extensive property with respect to time. And so that will be the approach that we will take in order to evaluate this. So what I'm going to do, I'm going to zoom in on that subregion that we had in our schematic. And we call that subregion 3 in region 3. One of them has Roman numerals. Okay, so what I'm going to sketch out here, remember this was bounded by, we had streamlines. So first of all, what color was our control system? Our control volume was red, so I'll try to be consistent with that. So the control volume was red. And then our system boundary, we drew that as being black. And we had streamlines, and I think the streamlines were in blue, so I'll draw this blue to be consistent. And this here is little region 3. And so it's a differential element. And this here is a streamline. And then we have our control surface on the left-hand side. So if we have streamlines on the upper and the lower, what we can assume is that the velocity vector is going to be parallel to those streamlines, between the streamlines. So the velocity vector is something like that. The other thing that I'm going to assume is the control surface, the area of that. It could be some arbitrary area. And what I'm going to do, I'll draw a projection of that area over here. We're not exactly sure what that shape is going to be, but I'll do something arbitrary like that. And I'll call that dA. So that's the projection of the area on the control surface. And it may turn out that the unit vector for that area could be a little bit different from the streamline and the velocity vector. So I will do that as area vector dA. And the angle between the area unit vector and the velocity vector, we'll call that alpha. And here alpha is less than 90 degrees for the way that we've drawn it. And that means that this is for mass outflow, or mass leaving our control volume, because this was on the right-hand side of the system that we were looking at. And the final thing I'm going to draw here is the length of this element that we're looking at, and we'll call that delta L. Okay, so I think that describes everything. Now what we're after is we're trying to determine, let's go back here, we're after this. So we want to know the time rate of change of the extensive property in region 3. So this is a differential element out of region 3. So what I can write is the differential element at time t0 plus delta t. So this is the differential element that we're looking at here, is equal to our intensive property rho times the differential element of volume in this little differential element that we're looking at. And we can express this then as the intensive property times the density multiplied by the volume of this is just going to be the area times the length. So the length was delta L, Now remember, the area and the vector itself might be a little bit off with respect to one another, and so consequently what I'm going to do is I'm going to put cos of the angle, because this volume is parallel to the streamlines, but the area itself might not be. And we need to be able to preserve that or take that into account. So that's what we're doing by introducing that cos alpha. And we get that expression. So out of that, we can then write that extensive property in region 3 at T naught plus delta T is just the integral of that over the control surface at 3. And what we're integrating is eta rho delta L cos alpha dA. And this would be at T naught plus delta T. Okay. So we're getting closer to understanding B. What we're going to do, we now want to find the time rate of change of that, because if we go back here, we're interested in the time rate of change of that extensive property. So that's what we're now going to do. And what we'll notice here is we have a delta L and a delta T. Well, if we look back at our diagram, delta L over a period of delta T, all that is, that's the velocity, the magnitude of the velocity. And so we can make that substitution as well, and we can rewrite it. And I'm going to write it as the magnitude of velocity, and then the magnitude of the area vector. So that will take us part way to understanding what's happening in B. That was term B. And then the final thing that we need to look at is C in our expression. And C, going way, way back, where's our diagram? C is describing what is happening in this region on the inlet. And so that's what we're going to work with now. So that was the expression that we had, and so what this translates into is basically what we need to do is come up with an expression for our extensive property at time t0 plus delta t in region 1. And just like before, what we're going to do, we're going to go back and we're going to take a look at the streamlines and at this little chunk or region 1 in order to figure out what is going on here. So again, we have our control surface, we have our system boundary, we have our streamlines, now the area here is going to be a little different from the way that we drew it before, because if you recall, area, we always have it projecting outward from our control system, and so this is the inlet to the control system, so the area is projected outwards, and consequently alpha, the angle between the velocity vector and the area, alpha is greater than 90 degrees, so this represents mass inflow. So mass coming into our control volume, and we have a projected area, some arbitrary area, we don't know exactly what it is, but I'll draw it as being dA. Okay, so what we need to do is follow the steps as we did for subregion 3, come up with a differential element. So eta, rho, our intensive property, density, but the volume is going to be the volume of this little element or differential element that we have here, so we'll just follow like we did before. And you might be wondering, why did I put in a minus cos alpha? That's because we want the volume to be positive. And we know with the way the sign convention is that it would come out negative if we didn't do that. So we put in a negative cos alpha in order to make it positive. And what do we end with? We end with an expression for the extensive property in region 1 at T naught plus delta T. We get that, but remember we're after the time rate of change of that, which is what C was. So let's re-express that. Okay, so there we have an expression for C. The last thing I'm going to do here, and notice that we have magnitude of velocity V and dA and cos alpha. Well, if you remember back from looking at mathematical operations, this is just the dot product. And we talked about that before, or the direction cosine. So wherever we have this, we can replace it with the dot product between the velocity vector and the area vector. Doing that, we take all of this back to equation 1. And so if you remember, this is A, B, and C from equation 1. We're going to plug them all back in now. You might be wondering how I got rid of the negative for control surface 1. The way that we do that, the dot product takes care of it automatically. We don't need to worry about it. So we can simplify this a little bit by saying that control surface 1 plus control surface 3, if you look back to our original diagram, that represents the entire control surface around the control volume. So we can couple those together and we can rewrite the time derivative of our extensive property, which goes into our basic laws. So this term here is a system formulation. And on the right-hand side of the equation, it has been recast into a control volume formulation. So we can use it then for control volume analysis by applying our basic laws, the laws of conservation of mass, momentum, be it linear or angular, and energy. Okay, so that's a lot of work to get one little equation, but this equation will be very, very useful, as we'll see coming up. This is sometimes called the Reynolds Transport Theorem. It links a system approach to control volume, so we can express the basic equations in control volume. So that concludes the derivation. In the next segment, what we're going to do, we're going to start applying this to mass, momentum, and energy.